Today on Diode. In this video, I'll be building a 900 milliwatt, 525 nanometer green burning laser, and it is glorious, along with showing you some of the other green laser pointers that I have and other things you can do with laser pointers, regardless of whether they are burning or not. I hope you learn a lot in this video and enjoy it. At the core of this laser pointer build, I'll be using the 1 watt capable NUMG525 laser diode, which puts out 525 nanometers of laser light. It's a 9mm laser diode with a ball lens on the top, and these are very popular form factors as they're coming out on the market. So the first thing I'll be doing with this laser diode is removing the top ball lens. Now there's a couple of ways to do this. Unfortunately, I did not know the easiest way when making this video, so I'll be using a very difficult way. But before that, I'm going to need to join those two pins together, so that way the diode is prevented against electrostatic damages. It's a very simple procedure. It basically just involves soldering the two ends of the laser diode together, so that way no voltage differential can be placed upon those two leads. In this build, I chose to use the Dremel to take the ball lens off the laser diode. Now let me explain. When I got the NUGM01 laser diodes, the 520 nanometer laser diodes, I had extreme difficulties removing the ball lens, so I used a small hand file to do this job. Let's see how this works. Oh, that was the worst possible thing that could have ever happened. This is probably the good time to tell you that in most cases you can simply remove the ball lens with the pliers by pulling it up off the laser diode. But until we find out whether my laser diode works, let's go see some other lasers, and even if they're not burning, have a little fun. This right here is a cheap 532 nanometer 5 milliwatt eBay laser pointer. So does it do any burning? Let's find out. Looks like you can see a little bit of smoke there, but not very much. Figure maybe this laser is actually putting out about 20 milliwatts, if not a little bit more, but that could also be due to the lack of IR filter. The reason that there's infrared laser light coming out of a 532 nanometer laser pointer is because they are a DPSS style laser, which stands for diode pumped solid state. And as you can see, when I interrupt the infrared beam, the green laser light is no longer coming out of the two crystals in the front. More about this in other videos. You may have seen or bought lasers with little laser star caps on them. Laser star caps actually have pieces of glass or plastic that are refractive materials, and these materials have little etched surfaces that are kind of like microprisms. But they're not the only thing that makes these interesting patterns. Here I have one of the 3-way LCD panels from a video projector. I have also tried using the TFT layer from a broken LCD, which makes some patterns, but I find them rather boring. To be honest, they really don't do that much. And one of my favorite things actually is to shine a laser against a computer chip, in which case I've used an Xbox 360 GPU, and the patterns are quite unique to every processor. Another thing you can do is use a pulled DLP processor, which generates a nice dot effect. Here are the 3 lasers in the 5 to 25 milliwatt range I have. Here's my laser diode after its short yet quick and flighty adventure across the room. There doesn't seem to be any damage on the little gold wires or the die, so it's probably still good. In which case, I'm going to press it in to the host. Pressing it into the host is actually a pretty simple thing. I am using a vise to apply adequate amounts of pressure to press the diode into the host properly, and I'm using a thick-walled aluminum tube, which gives me adequate pressure as well. Once I reach the press point where I can't push it down anymore, I can see if the diode is properly pressed in, and then put on my lens. This is a traditional MX9 threaded lens. That's a dual element lens, which means that this lens has 2 lenses inside. And here's the little boost board I'll be using. It's designed for blue lasers and is 3 to 5 volts in. It's also rated for 2.5 amps. In or out, I'm not really sure. Let's see how it works for green. Alright, and now for the tricky bits, setting up the laser diode to the laser driver. Right now I have my adjustable power supply set to 3.5 volts, which is the lowest voltage I will be drawing from a battery. With the lowest voltage found and a dummy load of LEDs, I will find two things: the rotation of my potentiometer and the lowest set point of my potentiometer. Once these are found, I can now connect my laser diode. The first step is to remove the dummy load LEDs from the laser diode driver. Once the dummy load LEDs are disconnected, I'll be taking my laser diode and connecting the laser diode negative to the negative output of the laser diode driver. Now that I have my laser diode negative connected to the negative output of my laser driver, I will be taking two sections of wire and a small terminal block. After I solder on the two small wires to my terminal block, I'll be putting them in the loop between the laser diode and the driver. This I'll be doing on the positive side. First, I have to strip off both ends of the two small sections of wire. I've also noted to use a thicker set of wires, so that way the current will flow through them more easily. The next step is to quickly solder on the two wires that I have to my terminal block and get ready to hook my meter up to them. I'll be setting my multimeter on the current setting so I can detect how many amps are running through the circuit. And once that is done, I'll be screwing both of my probe wires into the terminal block. Once that is done, I'll be connecting up the positive of my terminal block up to the positive output of my laser diode driver, and then the negative lead up to the positive input of my laser diode. With everything connected to the meter, I can now hook up my power. When I hook up power, I get about 1/4 of an amp or 0.25 amps going through the circuit. The next step now is to turn up the power supply from the 3.5 volt range to the 4.3 volt range, which will be the highest amount of voltage I'll be pushing through the circuit. And as you can see, when I turn up the power, the current going through the circuit also starts to climb. So right now we went from about 1/4 of an amp to a little over 1/2 of an amp. With the upper voltage range set on the power supply, I can now calibrate the potentiometer. Doing this can be quite tricky, and in this case for me, it's even a little bit more tricky because I can't keep the laser on while adjusting the potentiometer. This is because this high-powered laser diode gets quite warm during operation, and this module does not have a heatsink on it. So I'll be making small rotations to the potentiometer and doing short duty cycle tests to get readings on the meter. At this point, I'll also tell you on this particular driver and laser diode combination, I was only able to reach about 1.3 to 1.35 amps, which is actually short of the 1.8 amps this laser diode is capable of. But since it's going into a laser pointer, I was happy to settle with about 900 milliwatts instead of having a full 1 watt. And let's face it, I have other high-powered laser diodes, so it's not like I'm losing anything in the realm of burning. With my power supply and the long wires on my meter, I was actually only able to read up to about 1.25 amps. My laser diode driver does not have a switch on it, so I'll be using this N-channel MOSFET to control the negative current going to my laser diode driver. In which case, on the left side, I have my gate and my input wire for the MOSFET, and on the right, the out. I'll be connecting the drain or out of my MOSFET to the negative of the LEDs, connecting the source up to the negative, and using the positive to test the MOSFET circuit. For my build, I've used a piece of copper water pipe, and as you can see, I've tried to make an insert to hold my laser hose. Didn't go very well my first time around. And the reason why I need that insert is because the laser module itself doesn't hold in there very smoothly, very securely. So on my second attempt, I made a much better adapter to bring the tube diameter down, and you can see now my module fits inside rather snugly. I also made myself a little button. For the rest of the electrical bits, I have found and cut a slit into a piece of plastic tubing that fits into my copper one. After that, I put copper foil on the bottom of that tubing so it can make a good positive connection. Now, I can glue my MOSFET into the center of my assembly and check to see if it fits. Once all my positioning is set up and I can check my button spacing, I can glue on the top of my MOSFET a small 5mm tactile push button switch. After the switch is glued down, I can shorten my connections, which are the two wires. This red wire here connecting to the MOSFET gate, which connects to one side of the switch, and then a small section of wire that connects the other side of the switch to the positive of the copper foil on the bottom. Now that all the soldering is completed, I'm going to hook this assembly up to my dummy load LEDs and test to see if it works the way I want it to. Success. So much success. With the circuit tested, it is now time to find a spring that will serve as our negative connection to the battery. A little bit of trimming up along the edges to make it round, and I can connect it to the MOSFET string. This will be glued inside of the tube, and I want to ensure that it does not make any connection to any positive sides of the circuit. Once this is done, I can glue the spring into place. I want to make sure that the spring is as center as possible inside of the tube, so while the glue is still warm, I'm going to ensure its most center position. Once the glue had set, it was a matter of simply sliding in the assembly inside of the laser pointer. I also put in another piece of tubing to prevent the battery from making any kind of connection to the outside of the laser pointer other than from the bottom connection. On the other side, I have a red wire that is attached to the copper foil that makes contact to my positive connections and the blue wire coming off my MOSFET string. You'll also notice that when I press the button down from the outside, it actuates the 5mm tactile push button switch that's mounted on the MOSFET. Now, I had intentioned this laser pointer to fit a AA size lithium-ion cell, but I did not have one of those at the time when making this laser pointer, and sadly it does not fit in. So what I've done here is I've made a specialty bottom piece that goes in to hold the batteries in. It's actually made from a couple of vaporizer parts and laser pointer components that I had laying around. Even though I could not fit in a AA sized battery, I did come up with a little bit of a solution, and here's my positive terminal. Now, this can fit a AAA sized battery, or it can fit some of the e-hookah batteries, which look like this. Well, apparently that battery also looks like that. So, well, anyway, here's how this adapter works. So I can take off that extension piece, but never mind that. In this case, I'll be using one of these AAA sized batteries. Looks good. Time to connect up an LED to check to see if I get power out of those two wires. Success again! Now that all the electronics are inside of the laser pointer assembly, let's take some time out and talk about some other optics, how they interact with laser light, their uses, and what they're called. Here I have a piece of polarizing film, and with most lasers, depending on the orientation of which the beam enters, the light can be either blocked or passed. Some other videos feature a dichroic cross cube. Well, with diode lasers, you can also use a dichroic cross cube to combine two laser lights. If you notice, as I rotate the laser pointer, the laser is either reflected off at a 90-degree angle or passes right through. In some laser scanning assemblies, they use a polarized beam splitting cube, which looks like this, to combine two lasers together into one beam. If you notice, as I tilt it along the side, you'll see a diagonal reflective surface in the middle. With that little science lesson out of the way, now it's time to make the two final solder connections on my assembly for my laser pointer. This will involve taking off the test wires and then cutting to length the two wires that come out of my laser pointer assembly. The blue wire is my negative, which comes off my MOSFET drain. The red wire is my positive, that's connected to my laser pointer case. Once these wires are soldered, I'll be able to slide in the laser diode host into the laser pointer assembly. After those wires are connected, here's what the assembly inside looks like. As you can see, there's not much room in there to negotiate where those wires are going to go. So, let's start the final process of putting the module inside of the tube. For this laser pointer, I'll be using thermal paste. Because there's no actual heatsink in this laser pointer, I'll be relying solely on the copper tube I'm using as my laser pointer host. So, I'll be putting the thermal paste around the outside of the diode module assembly to ensure that I get the maximum amount of thermal conductivity between the two. The heat from the heat gun also makes the wires a little bit more soft, so that way they'll go down inside of the laser pointer assembly a little easier. I find this to be very helpful. Now that the laser diode assembly is fully inserted into the laser pointer tube, I can test it out. And it does work. I was quite happy to see that there was a lack of magic smoke flying out of the laser pointer. Now, I know the laser pointer really doesn't look all too bright, but to be fair, I am working under very bright shop lights. So, let's turn off the shop lights and see how bright this laser pointer actually is. Oh, it's very bright. The laser pointer worked. It was time for the finishing touches. So what I did is I spun my own cap cover on the lathe and got to gluing in a dichroic piece of glass. A dichroic piece of glass will ensure that no dust gets on the actual laser lenses. The oxide coatings on the glass will minimize internal reflections, and it will look really good from the outside doing it. I love dichroic glass on the front of my laser pointers. God, that looks good. That looks so good. Let's take a look at what this laser will be replacing along with some other really good looking lasers. This is my old 532 nanometer burning laser pointer, which used to do 150 milliwatts, but no longer does. Here are two other laser pointers that I put together. The top one is a 505 nanometer mint green laser pointer done in a gold finish. The one on the bottom is a 495 nanometer laser pointer, which is done in a rose gold finish. Both the 505 nanometer mint green laser pointer and the 495 nanometer aquamarine laser pointer put out about 50 to 60 milliwatts of optical power. These two lasers alongside my new burning laser simply look amazing. In the dark, you can see that the mint green laser is a little brighter in color. Meanwhile, the aquamarine is a somewhat deep bluish green color and looks rather astonishing in person. Here, side by side, are the colors of green laser light that I have collected so far, excluding the newly made 525 nanometer laser. And here it is in the dark. Now, you can see the laser beam, but this is shining against a black wall, so a lot of the reflected light is not there. But as soon as it hits a white surface, that dot becomes extremely visible. This thing easily lights up an entire room. But does it burn? Yes, it does burn. It burns really well. Now, enough about burning lasers and more about learning lasers. Have you ever wondered why a laser seems to sparkle no matter where you shine it? Well, if you'll notice, I'll shine an LED through this marble, and it looks pretty much like you would normally focus a flashlight. Doesn't seem to be any sparkle at all, or any kind of pattern. But if I shine a laser light through it, you'll notice that these weird patterns start to develop. Well, these are interference patterns, and they happen on almost every surface that you shine a laser against. In fact, I've gone to great lengths to try to show you this. Here's a picture of laser light against my wall, and underneath high-powered magnification, we can still see no real reason why laser light sparkles. However, on a completely smooth surface, And underneath my microscope, we can see the same interference patterns we saw before. These interference patterns can be made much bigger and differently distorted using lenses, different pieces of textured glass, and reflective surfaces. This is known as lumia. Now, as amazing as these patterns are, they require absolutely no computer. They require no video projector. In fact, all they require are different pieces of glass and a laser. Pretty simple, right? So go on and explore different pieces of textured glass and other things with lasers and see what you can make. I took this laser pointer outside to compare it to a 5 milliwatt laser, and my first thoughts were, this thing's stupidly bright and incredibly awesome. My second thought was, I'm Captain Obvious and everybody knows where I am. This thing was excessively brilliant. Look at this. Who needs a flashlight when you have a laser like this? Who needs a gun when you have a laser like this? This thing's ridiculous. The other green laser diodes I have are the NUMG525, which put out 525 nanometer laser light. And since this is calibrated to 1 watt optical output, I wanted to race it against my laser pointer. Let's see how it holds up. Wow, did you see how close that was? That was really close. I am not disappointed at that at all. Even though I was extremely satisfied, I did have a couple of 1 watt green lasers also out. So I figured we'll get 3 of them together on a piece of cardboard for a celebration. These lasers aren't focused on into a pinpoint, but I'm pretty sure they'll pack enough power to start some smoke going. Heck, with lasers like this, we can get away with such other barbaric things like knives and scissors. If you like this video, subscribe for more. I'll be posting up videos about DIY projects and science. As well, if you have questions or comments, leave them below. And as always, stay tuned for more.